emerging. Self-driving cars and robots are no longer domain of science fiction movies. They are now out of the textbooks and are emerging as one of the most amazing and revolutionary technologies of this century. In the factories, they are already the norm, and no one is surprised anymore to see a fully automated warehouse run by robots carrying material or even entire shelves from one place to another at a frenetic pace, never getting tired and never colliding. These robots are now coming out of factories and are heading straight to the doors of our homes. They will be the new postmen, the new couriers who will cross the city to deliver our order or our groceries to us. In this new, difficult, dynamic, and unexplored world, robots will have to learn to see, to sense the environment, and make tens of thousands of decisions per second. They will need to know where they are, where they need to go, which obstacles are there, and also how to avoid them. But more than that, they will have to learn to share their space with humans. When they will succeed in doing so, they will serve dishes at our table and will learn how to move in our world. They will learn about us, about where we are and what we want. They also will cooperate with each other, and they will probably become our loyal assistants. They will take us to work each morning, while we are carefully reading the morning news. And they will take us home at night, perhaps after a party, and they will always be lucid, alert, and reliable, and they will be able to see what we cannot see, and also to predict what we cannot even imagine. They will reduce the risks of road accidents and will save millions of lives each year, and give us the most important things of all, the time. The time to enjoy a journey, a book, a video, a landscape, while we are going where we want to be. They will take us to explore unknown worlds, will be our eyes and legs to observe places we cannot reach yet, and they will help to make those places closer and more familiar to us. But we are only at the beginning of this fantastic adventure, which starts on Earth, where the road for this self-driving system to travel is still long and packed with obstacles, so unpredictable and complex that they need your input and your ideas to learn how to help us and how to care about the things we care. The development of a self-driving system is an extremely complex and multidisciplinary process, which is why there are still no standard techniques or tools for developing such systems. Although one general-purpose technology has not emerged yet, the theory behind the working principles of these systems is already well known and well established, and often it is based on the theories that have been proposed centuries ago, but which then was also able to take advantage of the fervent rise of the new theories and new ideas in fields like machine learning and artificial intelligence. In such dynamic and still not fully defined scenario, the purpose behind this series of courses is to provide and convey the key concepts, the logic and the working principles of these systems. The frameworks or the programming languages that we are going to use during each course are just tools, just one of the possible ways of implementing autonomous driving algorithms. To make a comparison, they are just tools that the mechanic uses to repair a car, for example. Given that, you can easily take this series of courses even if you haven't mastered the programming languages or the ROS frameworks that you are going to use along the course. I will take care to explain the logic of the code that we are going to develop together during the laboratory lessons, and also I'm going to explain how each of the ROS components works before using them in the courses. Furthermore, you may also decide to follow me through the courses using a different framework, such as ROS2, or even using a different programming language if it's more familiar to you. The philosophy of this series of courses is to learn by doing and by quoting Dale Carnegie, learning is an active process. We learn by doing. Only knowledge that is used sticks in our mind. Namely, the best way to learn and master something new is to actually use it in the real world and create something new, something unique and personal that is the result of your creativity and the application of your knowledge. For this reason, during the course, we are going to create together a real prototype of a self-driving robot, on which we are going to apply the concepts learned during the theoretical lessons and on which we will experiment and test new ideas. Still, if you don't have the hardware or the tools needed to create the real robot yet, don't worry. During the course, you will also have a simulator of a self-driving robot that will allow you to reproduce the behavior of the robot just using your PC, without any additional hardware. I suggest you not only to follow the lessons and reproduce the steps, but also to take a break from time to time and experiment your ideas and use the concepts you learn and make it yours. I will provide you with all the tools and I will explain you how to use them to make your idea come true. Hi self-driving enthusiast! In this journey that we are about to begin, we will address all the major aspects involving the development of an intelligent self-driving system. In the first course, we will start by studying the motion of a self-driving robot, and we will implement the equations that allows the robot to translate some given velocity commands by using a joystick into wheel control commands. This branch is called differential kinematic and is the foundation of all the movements that the robot is capable of doing. Next, we will address the inverse problem of the differential kinematic. In fact, in this section of the course, based on the information coming from the encoder sensors that measure the rotation of the wheels, we will try to estimate the overall motion of the robot. This field of study refers to the odometry computation and is essential for the estimation of the robot's position during his movements. Then we will see how to improve the robot's odometry and thus to provide a more accurate estimate of the robot's movements and consequently also improve the estimation on the robot's position by fusing data from multiple sensors such as encoders, accelerometers, and gyroscopes. In this section of the course, called Sensor Fusion, after a brief introduction on the probability theory, we will address the problem of the sensor noise that affects all the measurements in the real-world sensors, and we will implement a Kalman filter to limit the effect of noise. By the end of this course, you will have a clear understanding on the odometry and control in a self-driving robot. In the following course, instead, we will talk about mapping and localization. Here, we will use the same robot with the integration of a laser sensor to map an indoor environment such as your home. First, we will assume that the robot perfectly knows its position while it moves through the environment, and in this case, we will only use the laser scanner to extract a map of the environment. Then, after generating the map, we will use it to localize the robot on this map. Finally, after addressing individually the problem of mapping and the problem of localization, we will address the more complex problem of SLAM, that stands for simultaneous localization and mapping. In this section of the course, the robot will simultaneously use its sensors to localize itself into an indoor environment while extracting the map of the same environment. At this point, the self-driving robot will be able to know what the world around it looks like and also to localize itself within it. So, in the third course of this program, we will address the problem of planning and navigation. In this third course, our self-driving robot we'll have to learn how to plan trajectories to reach a goal, namely how to reach a desired location on the map, starting from the current position of the robot. Here, we will develop together several path planning algorithms, and we will compare them to investigate their advantages and disadvantages. Then, while executing the planned trajectory, the self-driving robot will have to constantly sense the environment in the event that an unexpected obstacle blocks its path, and will need to make appropriate adjustment to its trajectory in order to avoid the obstacle and still succeeding in achieving its goal. Furthermore, during this course, we will implement flexible navigation techniques, and we will develop more complex navigation logics through the usage of behavior trees. The last stage of this journey will take us in the world of computer vision. In this fourth course, we will integrate a new sensor to our self-driving robot that is a camera, which will provide more data for a more complete knowledge of the world around the robot. We will use this information to implement visual odometry algorithms that can estimate the robot's movements and thus its position by analyzing the stream of images coming from the camera. Next, we will use the image stream not only for localization purposes, but also for mapping by detecting features in the environment and then implement visual SLAM techniques. Finally, we will implement a system for the detection of moving obstacles and a tracking software that will move the robot so that it follows any moving object in the scene. As you may have noticed, in this series of courses, we are going to use the same robot that we are going to make more and more intelligent by adding new software and new sensor along the different courses. Although I recommend you to take these courses in the order that they are presented, this is not mandatory since each course is designed to be independent of each other and will provide you with all the knowledge and the background that you need to succeed in the singular course. In this course, let's talk about odometry and control.